Hello all. So I'm going to talk about AAWA program, which is one of our research programs and one of our programs which has been running for longest on this field. We started AAWA in 2015. Back then it was still the first programs talking about autonomous shipping. One of the first ones was Moonin program, EU-funded program was in 2014 and 15. And this is the first one looking actually operating a vessel as well in that sense. Last Tuesday we announced that we have first commercial vessel we are already controlling remotely. So I'm going to focus on this one and more on the autonomous operation and not so much on the remote operation. As a company we have stated that remote operations for commercial vessels will be coming in 2020. But as we saw last week, we have now made it in reality faster already. So now we are in a situation that we have one tugboat in Copenhagen, which we can commercially operate also from land. And it is a fully safe system, and it has been demonstrated as well in that context. So our program is a Finnish government-funded research program. It is totally 6.6 million euros in funding, and it's mainly funded by TEKES, which is the Finnish Innovation Fund. As part of the consortium, when we started this, we had 3 different objectives which we wanted to highlight in the beginning. First of all was that we need to create competence for remote and autonomous vessels because there isn't anything in that context. And in this context, we are talking about remote and autonomous vessels and not just boats. There are vessels, small boats, already in commercial operation as well, but those are mainly in the size of less than 20 meters. So what we are talking about is a ship-sized vessel, which is for commercial operation, and developing solutions which are feasible for those. There are vessels also in naval sector used, but the challenge there is the cost factor. So commercial vessels and naval vessels have a slightly different OPEX and CAPEX profiles as well. Another thing was that we wanted to create a hotspot for developing these solutions. So we wanted to create this kind of ecosystem around autonomous shipping in Finland. And for that we have created a consortium called 1C, and I believe there will be a presentation by DMAC, which is the Finnish industry consortium, presenting that later on today as well. And then also we wanted to look at the commercially viable solutions in short term, so not just focusing on the 2030 autonomous shipping, but also focusing on what can we have in the next 5 years, what can we have in the next 10 years, and create roadmaps for that, and bring out solutions in that respect. These are the different partners in our program itself. So as the main classification society involved, we have DNVGL, so that is the Norwegian Den Norske Veritas, and German Lloyd, which went together some years back. We are leading it from the technology side. Then we have, in addition to ourselves, Inmarsat, who are working on the satellite communication and handling that side of things. Delta Marine is a Finnish ship design company, and they are handling the ship design and feasibility studies for vessel. Napa is an optimization system provider from Finland as well, owned by Japanese class. And they are working on the safety systems of vessels and making the risk analysis side of autonomous shipping. Then from research partners, we have VTT, which is the Finnish Research Institute, similar to Fraunhofer here in Germany. OPA Academy is looking at the legal studies and legal side of issues. Turku University is focusing on machine vision and to some extent also on other technology aspects. Tampere University is working on autonomous navigation and robotics, and Aalto University is focusing on safety and risk assessments and financial side. Then we have also 2 operators, vessel operators involved. ESL Shipping is a bulk operator in Baltic Sea. They mainly operate and transport raw material from mines and steel factories to Baltic region. And then Finferries is a ferry operator who is operating all the ferries in Finland, in the archipelago and also inlands. So it's a quite big variety of different companies and different universities and also different customers. And the objectives of our program and the research areas which we are focusing is very wide. And in that sense, we are one of the widest programs is because we are focusing on technology, but also on safety and security, social and legal acceptance, and business models and economy. So it's not just looking at one aspect of the autonomous shipping, but the whole big picture. And we are benchmarking everything that we do against what has been developed elsewhere as well. And the results we have, we released after the first year of research work a white paper, which extensively goes through all the small details of what are the kind of needed changes in legislation and so on. And that white paper can be loaded from Rolls-Royce website as well. And if you just write into Google our white paper, you will find it from there as well. And there will be a second white paper coming out at the end of this year to conclude the program itself. So technology-wise, what we have been focusing on is the situational awareness and autonomous navigation systems. And going in a bit detail on situational awareness first. So what is situational awareness? It is fusion of data from different types of sensors. We do have one ferry which is fitted with situational awareness system. It is operating in the Finnish archipelago, mainly transporting people from mainland to islands. And that vessel is equipped with a wide variety of different sensors, and we are running sensor fusion of these sensors on board. So from sensor side, we have 2 high-resolution cameras, so normal cameras, 2 low-resolution cameras with infrared capability, 2 middle-range marine radars, and 4 short-range radars from automotive side. And then we are also trying out LiDARs. And the LiDARs we are using is slightly different from automotive side, as we are using long-range radars, which have the capability to go up to 1.5 kilometers in distance. So by fusing all of this information together, we are then providing the whole situational awareness of what we see around the vessel itself. And just to make things complicated, this is the kind of pipeline chart we are following up. So first we process the information and then process the radar and LiDAR data on top of the camera feed, and then combine all of this information into a single map, transfer everything into radar coordinates, import the IDs of different identifications we have made, import that information to object list, which is then used for autonomous navigation, and then we do classification based on the objects themselves. All of this sounds very fancy and complicated, but I can show it from videos to make it a bit more simple. If you put on the first video. So in this video, you can now see the detection from directly from video feed. So the different colors are highlighting the different detections and the different systems making the detections. So if there is, for example, classified object, it is on kind of a lime color. So that means that our system can identify with 100% certainty or 99% certainty what it is. And then in addition, it is detecting different things all the time in the surroundings as well. And there is, for example, behind the island, there is a sailing boat which we are identifying from the mast. But because if we're only seeing the mast, we're identifying it based on 30% accuracy that it is on a sailing boat, or it could be something else. And then if you press on the second video, so that was during daytime, and then this is during nighttime, the same thing. And on this one, there is a boundary box of infrared camera, just showing what you can see. And then the total blackness is the normal outside of the scope, which you wouldn't see with your bare eyes either. But in this one, our machine system is detecting everything in the distance as well with small lights and reflections. And it can see much better than human eye in that sense. And this is essential information for autonomous navigation. So when we don't have anyone on board, we need to have automatic systems that can do this kind of detection. So what SA is about, it's about sensor fusion. It's about the camera-based sensor fusion and providing the operators reliable data on what we have around us. And then based on all of this information, we create a map for the autonomous navigation to make decisions on what it sees and what's around it. And then this is then used for our collision avoidance algorithms to detect how our own vessel will behave in respect to these other objects out at sea. And this is what the map looks like. So here is, as an example, we have, from the big picture, we are creating a 2D map. And then in a map, we have locations where we are detecting different things. And all of these different items have different size information. So we are showing which items have, or which sensors have detected them. like the one we have highlighted. This one is ID 1834, and it is 319 meters away from us. It has no velocity, so it's fixed position. It has heading of 180, and the size is 80, and we have drawn a boundary box around it, so we have identified that. So in that sense, there is something which is quite significantly big, but it's still some way ahead. And then from LiDAR, we can say that it's 3.6 meters high in distance as well. And it is the marker we can see in front of us. It's the C marker. And then we are also seeing it with our Mobotics cameras, and the width there is 1.2 meters. So we are detecting an object which is relatively big in height, but narrow, and it is not moving anywhere. And then with FLIR, we are also verifying the size. So now we have quite good understanding what's ahead of us. And then when we feed this information into our autonomous navigation system, we can quite confidently react to that one and be sure that it's staying on spot and it's not moving anywhere. And we can make our maneuvering decisions based on that information. Then going to navigation systems itself, it defines the status of the ship relative to other ships, using SA system as one of the base foundation systems, but also the weather condition and monitoring data from a vessel itself, like health monitoring and condition monitoring data. And the system ANS takes control of collision avoidance and needed actions from the vessel itself. These are the four main elements of the ANS. So we have the status definition, situation assessment, collision avoidance, and route planning. And all of this information is relayed to control system and to operator on shore as well. Going in first into the situation awareness system, so that will determine what kind of actions we should take. Should we give way, stand on? Are we on a head-to-head collision course? Should we overtake someone, or are we being overtaken? So this is what is happening in relation to us and the other ship. And then the navigational status definition is then looking at the whole big picture. What is the situation awareness of the vessel? What is the conditions around the vessel? What is the conditions of our own equipment? And what are the weather conditions? Because all of these have an effect on how our vessel will behave and how the other vessels will behave, and what is the total big picture of the situation prevailing. Then, if required, we may need to go into route planning, and we need to change our route from the predefined one. And then in route planning system, we can make new waypoints, because there are situations where the autonomous system cannot make all the decisions. Then the information is relayed back to operator in the operating center, and then they may need to take an interview and take actions on the navigation course of the vessel. For example, if there is a situation and you have 5 different vessels coming at you at the same time, and the system just cannot decide on its own where to go because all the options are as bad. So then in that case, we give the decision power to the operator, and then they will make the end decision how to go from there. And then the collision avoidance system, that is defines the routines for collision avoidance. So as normal, we need to oblige to collision avoidance rules and regulations. And then there are also situations where everything is based on good seamanship, but it's really difficult to code in good seamanship. So that's something we need to, in some sense, trial and error over time. So we're developing that side of the system all the time. And situations like this is if you follow collision avoidance regulations, sometimes you need to make the decision if you run aground or if you jeopardize the regulations and go against them. Yep. So here's just a few scenarios from our simulation, how the system is behaving for different changing conditions. The first one is changing speed. So you can see the different colors are our force vector, and the blue is the object coming to us. And in this case, we're just slowing down enough for the vessel to bypass us, and then we just accelerate again. And here we have a situation where someone is cutting ahead of us. So we are just slightly reducing our speed and then waiting for it to pass and then accelerating again when we have a safe distance. And the small lines you can see, those are our reaction lines. So that is the kind of maximum turning circle we can take. And in this case, we are then overtaking another vessel which is ahead of us. We're first making automatic replanning of the route and then following our corrected plan. And then the one in the front, you can see also the power of the vessel. And then replanning the route. Now we have 3 different vessels on our way. So we are first accelerating. We have 2 other vessels we can see. So we need to replan and go around those in a controlled manner and have a safe distance to other vessels as well. And then in some cases there may be a need for emergency maneuvers like crash stops. And in this case it's a full crash stop situation where other vessel is heading directly towards us. And we need to just stop all of our operations immediately and go to either electronic anchoring or then continue after the incident has gone away. So there are different scenarios, and these are just the base scenarios we've run on simulated environment, and we're running these also on actual vessels as well. So, but there is a lot of different things to be taken into consideration into these as well. Way forward from technology design point of view is that we are continuing the optimization work on algorithms, because the algorithms and detection algorithms are highly dependent on the weather conditions. So we're trying different algorithms in different weathers around the world. So we're running tests in Nordic areas for Arctic conditions, but also in tropical conditions as well. Then we're also optimizing the processing pipeline. So we are trying to make the data bandwidth usage as optimal as possible between the connectivity from vessel to shore, but also what is needed from processing power on board the vessel itself. And then also we're running hill testing of the full system. So in hill testing, we run fully simulated tests on all the hardware and software systems in the technology itself. Then if you look at the other research areas where we are focusing, so safety and security-wise, one of the key things is that vessels shall be in future at least safe as they are today. So that is the kind of baseline. And there is a potential to reduce the human element. Human error has been, by different studies, it's contributing of 60 to 89% of accidents. So it's a main contributing factor in that case. But then yet again, there is no study showing how many accidents have been avoided because of human factors and the human element being on board. But as a baseline, it has to be safer than the vessels are today. And that's why we are, for example, rolling out first safety-related solutions, like the awareness system. It's now installed on existing vessel as an advisory system for crew on board to help them to see better in dark, to operate their vessels more safely. Social-wise, what we have seen, for example, in LNG is that if there is a political will to change regulations, those will be changed, and those can be changed quite fast as well. And that is something we're seeing on the autonomous shipping as well. Just a couple of weeks ago in the IMO safety session, the work was started for starting to change the IMO regulations towards autonomous shipping, which is a very important stepping stone in the journey to future. But in that sense, it was also acknowledged by the that although the legislation is coming behind, it is still important that the technology development goes forward, and it's not being stopped because of the legislation not existing. So that's an important thing. And we are running different kind of studies on the legal issues. For example, can there be an unmanned bridge? Is that allowed by legislation? And if it would be, can we have a notation for periodically unmanned bridge, like we have in ships for unmanned machinery spaces already? And then also we're looking at the liability side. We're also benchmarking a lot to automotive industry, but the main difference there is that ships do go from port to port, from nation to nation, and cars usually stay within 1 or 2 countries' areas. So in that sense, if you make a liability regulation for cars in US, the same doesn't apply for a ship which is going from Europe to US. So it's totally different regulations in that sense. But we are trying to keep up to the automotive side as well and to learn what are the new things they are kind of coming up, because liability will be one of the key things and it will be one of the main factors for insurers in that sense. Then economy and business models. So when we started this autonomous journey, not that many were keen on talking about autonomous shipping. It wasn't so popular topic. But what we have seen now during the last year or so is that everything has changed 180 degrees. So everyone's now very pro-autonomous shipping and wants to develop solutions. There's a lot of new players coming into this market, and it is now more acceptable than it was 2 years ago. This is the phases we are running. So in the phase 1, we first defined what is our program itself. And now last year and this year, we've been developing the solutions and doing the focus research. And next year, we'll be running a proof of concept on the development work on a sailing vessel. So next year, we'll be operating one vessel autonomously with the research work we have carried out in this one. So that was my short introduction to this research program, and I would like to thank you for this opportunity.